Welcome back. The plan for today is talking about the cache and then moving on to the next module. If you remember the last, by the way, any questions before we get started? Yeah. Next week is what? Oh, yeah, I'll talk about the plan for next week. Okay. We will finish this and then we'll talk about the other things. So this would be also included in your quiz, just FYI. So we talked about cache design and various different ways of you can map and how you can improve the cache design and so on. The final thing that I wanted to talk about was how to optimize the cache. And remember that I told you that essentially from the CPU's perspective, what we are trying to achieve is reducing this average access time, which then in turn means that you're reducing one of these three categories: the hit time, the miss rate, and miss penalty. And we started talking about how do we optimize each one of these. We started with reduced miss rate. We talked about blocking and block size and how blocking can help. What we said that essentially you don't want too big of a blocks as well. So you want to increase the block size, but the block size has to be somewhat manageable. You don't want to have massive block size because that also results in what we call cache pollution. Then we talked about associativity, which we already kind of talked about fairly extensively in the previous lectures of like fully associative, set associative, direct map. For set associative, we said that essentially increasing associativity at some point will not going to help you any further. The reason for it is, the number of conflict myths is going to be saturated, and the only other things is the capacity and the compulsory misses. So some form of a balance between the number of ways and the design is needed. Obviously, we say that larger caches helps to reduce the miss rate. What prevents us from having the larger cache is two things. One is the technology itself, and the second thing is that increasing the size of cache can have diminishing returns in cases that most of your misses are compulsory misses. So not necessarily increasing the cache is gonna have a positive impact. The negative impact of increasing the cache size is hit time increases, because if the cache is larger, it takes more time to read off of it, mainly because of the capacitance. Longer, more rows increase the capacity, the capacitor of the read lines, and as a result, it usually takes more time to read things. And then I think the last thing that we were talking about last Thursday was prefetching. The idea of prefetching is that since we have lots of compulsory misses, we can maybe predict the patterns and bring those blocks from the lower stage or lower part of the memory into a closer to the CPU, like level 1 or level 2. A very simple example is this strike prefetcher or next line prefetcher, which if you see a pattern like this, then you can easily predict that the next one is going to be I plus 5 or I plus 4 or I plus 5, and then bring that data into the cache. Okay, this is what we call prefetching. You have to be careful about prefetching as well, similar to others. You want to bring things, but you don't also want to bring a lot of things, because if you do and you don't use them, or your prefetcher logic is not very accurate, then it will lead into cache pollution again. So from prefetching, you have to be careful about that. For prefetching, you need to answer 4 specific questions. What addresses should we prefetch? When should we prefetch them? Because the timeliness of prefetching is very important. For example, you may be able to predict that a particular line is going to be used, but if you predict it too late, that line is already requested by CPU and hasn't been fetched properly, so your prefetcher is not going to work. Also, if you prefetch too early, you bring something that is going to take thousands of cycles to be actually accessed. That's also not a good idea, because during that window, you could have saved something and stored something more useful. So right time for the timeliness of your prefetch is very, very important. Prefetchers also, as I said last time, it's important to where you want to put your prefetcher, right? So for example, do you want to put it in L1 cache, or do you want to put it in lower level cache? So for example, say that, okay, I kind of think that this is going to be used. I'm not sure when and how much. So I'm not gonna like occupy my precious L1 cache, but maybe I put it in my L2 cache because I have more space there. Second thing about prefetching is you can put it as an LRU, or you can put it as MRU, or you can put it somewhere between. So that's also you need to kind of decide, because there are other lines that may or may not kick this out. So you want to protect it somehow, but also you don't want to kind of like put it as LRU, because that might be the too much of a priority. Yeah. Cache itself has multiple layers, as I'm going to talk about soon. So like you can have level 1, level 2, level 3 caches. Yeah, the question was like, do we have multiple, why do we have multiple level of cache essentially? And lastly, there is like, how do you want to implement your prefetchers? There are two types of prefetchers. There are what we call software prefetchers and hardware prefetchers. Software prefetchers are actually, you can think about them as instructions. So we can actually put an instruction like load this address, and that would result into a load. And this load address could be for future addresses, right? So for example, think about like a code sequence like this, that for example, at the moment we are reading, let's say I1, like I is equal to 0. So we are reading like A0 and B0. But what we can do is that we can, for example, if the next one that we're going to prefetch is the next 8 blocks, we can also put like, oh, okay, when I'm reading A0 and B0, please also bring A8 and B8. And the reason that these are 8s is because we have blocking. So essentially, when we are bringing 0, we also bring in 1, 2, all the way to 7. And when we are prefetching 8, we are prefetching 8, 9, all the way to 15, okay? But generally, this could be also like I plus 1, doesn't matter. But what it says is that when I'm reading the current line, I also put a prefetch request to bring the next line. So the prefetcher essentially not only schedule the current address, but it also bring it. And what will happen is that the next iteration of this loop, when I is actually equal to 1, we already have this data. So this would be a cache hit. And we're also going to bring in the next sequence, which is, for example, I plus 16 or so on and so forth, right? So this will give you kind of like, you always one step ahead of what you're actually going to read, because you always ensure that that data is already in the cache and you're one step ahead. And this is nice because you can actually implement this as a software programmer. So you know exactly what patterns that you're going to do. So this will guarantee very, very accurate prefetching, because you are the one who is actually, producing this sequence. Okay. This could be also used for something like a linked list or more complex kind of a pointer chasing algorithm. So if your system is also some form of a pointer chasing or a linked list, you can also prefetch the next pointer and do the similar things. And this one particularly is actually very hard for any sort of hardware prefetchers, because your pointers might be scattered across different parts of memory. They may not have like a very deterministic sequence of addresses, but you know exactly where your next pointer is, and you can always prefetch that. So this prefetching could happen in software. There are actually, in some ISAs, there are instructions specifically for prefetching that you can use. So this kind of line of work, line of code is actually translated in the compiler into an instruction with that address. And as I said, this makes it very easy for a programmer to generate this, makes it easy for the hardware to understand it as well. Uh, Things can also be implemented in hardware because essentially in software, you're shifting the burden of prediction to the programmer, and the programmer may or may not be familiar with this sequence. So hardware can also predict this. Yes. Yeah, so when you're writing this code, you're actually inserting these two lines, right? Yeah, so when you're writing, so this is like a C code, for example, that you can actually insert these lines. Mm-hmm.
Since it's a sequential loop, do you like basically based on the algorithm just and like try to
Yeah, you can do anything you want. So you can anticipate that, okay, I don't, so when I reach to I minus n minus 1, then I no longer needs to prefetch, right? So you can also like add an additional if. There's also trade-offs, right? That you are adding additional branch, so is it really worth it? Because you're only bringing one block. So probably you don't want to do that, but you can. You can also do this for like n minus 1 and have another line here that says sum of like something like a n times bn, something like that, right? So you can have a one extra iteration yourself if you don't want to do the prefetching. But these are all like a C code level, like a high level, programming language level. Okay. For hardware, as I said, you usually also implement things in hardware. Most of the modern processors have prefetchers in hardware as well. The one that is very popular is what we call a next line prefetcher. That essentially what it does is bringing the next n lines, and n is the parameters that you can set in your prefetcher. N could be 1, it could be 8, it could be 16, depending on how much you want to bring. And usually this is fairly advanced, which means that it can detect different ways of next line. The easiest one is like I1, I2, I3, I4. But let's say if you also have some form of a bigger stride. So for example, you skip odd addresses, it can also easily predict and find that, right? So if your addresses are like 1 and 3 and 5 and 7, it can predict the 9 and 11 and so on and so forth. So this would be next line or stride prefetchers in some cases. Very simple to implement actually in hardware. It's not that difficult. All you need to do is some form of a history of the previous 3-4 addresses. And then if the difference is the same, you prefetch that. You also don't need for sophisticated pattern detection. This is just stride, right? And works really, really well in many cases because like, scenarios like this that you have like a for loop or a while loop that just kind of go through data one by one. These are very common in writing codes, and it's very easy for the prefetchers to detect them. But of course, if the patterns are irregular and your next line somehow thinks that it needs to bring things, then it will result into cache pollution and lower miss rate. So it's not going to help you. It's actually going to negatively impact your system. So as I said, you can improve this by having what we call stride prefetchers. That is not necessarily +1, +1, +1, but maybe +n, +2n. You can actually predict any sort of weird patterns if you want to. There is also another thing that is called stream buffers. That let's say you're not really going with like a specific pattern, but you're doing something like address A, then address B, then address C, then address D, and then you kind of repeat this. And if I again remember this sequence of the stream, then I can also predict this. Even if the A and B are not relevant, it could be just random addresses in the cache or in the memory. If I keep repeating this sequence of addresses, I can remember that stream and also prefetch that. So again, prefetchers are very sophisticated in detecting these patterns as well. Okay. So yeah, so to kind of like summarize, prefetcher helps you with predicting the access patterns, bringing the data right in time, reduce the compulsory miss. But on the other hand, the downside is cache pollution. Yes.
wait, so what this next line is saying back to that address, and lines from there.
Yeah, whenever we have an axis, not even a hit, when we have an axis, you predict you bring the next n lines.
What's the next end line? Not from like where that address was.
Yeah. So that address is a physical address. Let's say 1000, right? So what you would do is you bring in 1001, 1002. But just keep in mind that we also have blocking, right? So if the blocking also there, so for example, let's say you have blocking of 4, which means that when I'm bringing 1000, because of the blocking, I'm also bringing 1001, 1002, and 1003 anyway. So it's nothing to do with prefetching. I'm just bringing those 4. So in that case, prefetching means that I'm going to bring 1004, 5, 6, 7 as one block, and then another block, and so on and so forth. So blocking and prefetching can work hand in hand. Yeah.
So like what it does is loads like address into the
Yeah. Yeah, think about it as an additional load. It's a load that is not generated by the software. It's a load that is generated internally by the hardware itself. So it's like a LW, for example, address X. Think about it now, we are putting one underneath it that is also LW address X plus some N, okay? And then basically both of these will be handled by the CPU. The first one is time critical, so you need it now. The second one is not going to happen maybe in 100 cycles. So it will go into your LSQ, it will be read by the memory. All of these things happen in the background. And by the time that you actually access X plus N, now you have it in a cache. So it would be a cache hit. All right. Any other questions about prefetching? Great. Another way of reducing the miss rate is what we call a victim cache, okay? So victim cache is a very small cache that sits between your current level of cache and lower level of cache, or the main memory, whatever it is. And what it does is essentially remembering the last few lines of cache that you have evicted from the current level of cache, okay? Think about it as like a history of your browsers, as you like remember the last 4 tabs that you closed. Similar idea, that it's likely that like the very recent things that you kicked out, you're gonna use it in future. So it's kind of remember those tiny bits. Of course, you cannot remember everything, because essentially if you remember everything, that becomes the cache itself. But this is very tiny cache, usually like 4 to 8 entries. That's how small it is. But you can just remember the last 4 things or last 8 things that you have evicted. The nice thing about this victim cache is very, very useful when you have conflicting addresses, okay? So if I have like, let's say I have a 4-way set associative cache, okay? And I have 4 addresses A, B, C, and D that all map into the same set. So they are nicely fit into this cache. But let's say now I have something like, E and F and G as well that also maps into this cache. So what will happen if I have like a sequence that is kind of like go through this and go back? So A, B, C, D, E, F, G, A, B, C, D, E, F, G, okay? What will happen is that these guys are gonna kick these guys out. So we're gonna have a lot of misses because we don't have enough space, they don't have enough ways to store this data. But if I only have like 3 or 4 more entries in this victim cache, when I have A, B, C, D, and then E, F, G, when I'm, for example, kicking out A, B, and C, I put A, B, and C here, right? And then I will have all the hits, because essentially E, D, E, F, and G all inside the cache. So these are hits anyway. And then when we are going back to A, I will have it in the victim cache, and that would be a hit as well. So you can kind of think about your victim cache as some form of a reserved extra weight that can be added to any of the sets, because in the victim cache we do fully associative. We don't do any sort of mapping, so we can store everything everywhere. but it's available on demand to any of the sets. So we can essentially virtually increase the number of ways within each set based on the size of the victim cache. The hit time of the victim cache is pretty close to the hit time of the actual cache because it's very small and very close. It's not as good as the original cache. So for example, the hit time for A's is slightly higher, but it's significantly better. It's significantly better than the next level cache. So that's where the benefit is coming from. So for example, if the hit time for level 1 cache is 1 cycle, the victim cache is maybe 2 cycles, versus the next level cache would be 10 cycles or 20 cycles. Yeah.
What's the difference from victim cache compared to just any cache space?
So good question. So why don't we just add more space here instead of using the victim cache? The reason for it is that this will only add you one more set. It doesn't solve you the problem of conflicting. Because like, scenario like this, in order to fix this scenario, you need to add sets to all. So you need to add more ways to all the sets because you don't know which set this is going to be happening, right? Versus victim cache is essentially oblivious to the set. It says that whatever you're kicking out, I'm going to store it. So today might be set number 1, next day might be set number 20, next day might be set number 31. So it's much more strong. It's a much stronger design because it can be assigned to any of these sets. Yeah.
So it seems like the other sets, you want this critical path to help it out. And it is the amount of set of access out of like brings it get out, go back and forth. Like I'm thinking if you have that go out to different sets, then if that's something that can happen, that is a critical time. How would you go?
So yeah, so of course victim cache is not going to fix all the problems. So the question is, if you have 2 sets like this, then like another set of A prime, B prime, C prime, and then I don't have enough space in the victim cache, then things will also kick each other out inside the victim cache itself. And for sure that could happen. This is just a notion, this is a probability. The probability of something like that happening is very low. So you're saying that, okay, it's very likely that I have like 4 or 5 addresses that are conflicting each other. It's very unlikely that I have 2 sets, both of them have this kind of conflicting. But it's, of course, it's possible. In the victim cache, you also kick things out, so you're not going to get a very good performance. Yeah, and then another very useful things for victim cache is it makes your direct map cache like a set associative cache, right? So you can actually have just only 1 row per, like 1 way per set, which is a direct map. And now since I have a victim cache, essentially I can absorb some of the conflicts because now I have the victim cache. So for example like this, that I have a direct map and I have 080808. Remember that when we only had the direct map, this was all misses. Now if I only have like a victim cache with even 2 entries or even 1 entry, that would be more than enough to make sure that this is all hits, right? So the first 2 will be missed, afterwards will be all hits. And this will be inside the direct map. And you remember that direct map was a very nice design because it gives you very, very fast hit time. So this is kind of compensating the direct map even more. So direct map with the victim cache is a really, really nice design. It's being actually used in many like modern systems. Okay. Yeah, and then people, as I said, victim caches are actually pretty small. Usually a 4 entry cache can reduce 90% of conflict misses. So it's very significant. The downside, of course, is the extra overhead and more complexity because now your miss rate, so your misses now needs to go to the victim cache and then from the victim cache goes to the next level. Your miss penalty is slightly more. So there are these other problems that are going to happen as a result of victim cache. But again, a trade-off that since it's reducing, for example, conflict misses by 90%, this might be a good trade-off to make. Okay. Lastly, for miss rates, you can also use other things such as compiler and software. Yes. What's the difference between adding a victim cache and adding 4 rows to the cache? It's kind of similar to the question that was asked. As I said, if I add just 4 more rows, I'm not fixing the conflict for this row, for example, right? So this row, if you still have conflict for that row, adding more rows is not going to help you. But victim cache is going to help you with adding conflict in any row. So if I have a conflict here, things will be spilled into the victim cache. If I have a conflict here, things will go into the victim cache. So you are assigning extra rows to virtually every other row in the existing cache. That's the difference. Direct map cache, it could be also applied to set associative to virtually increase the number of ways in a set associative. Either way, anything that results in conflict is can be improved by victim cache. Yeah. It is technically, so the question is like, how is it different than L2 cache? It's technically another level of cache, but it's very small, right? It's only 4 entry. And it's very close. So the hit time of victim cache is close to L1. It's not L2. As I said, for example, victim cache delay is. It's a lower, yeah. It's a definitely. I mean, technically, it's like in between the 2 levels. So you search the first level first, then the victim cache, and then the next level. So yeah, it's kind of like a 1.5. Think about it that way. All right, so compiler and software can help you. I already show you that, for example, you can issue prefetching inside the code. You can also reorder your arrays to increase their locality. You can combine loops in order to reduce the number of, combine the loops with similar behavior to, again, increase the locality. There's this thing called tiling, which allows you to kind of like work in a smaller subgroup of your matrix, allowing you to, again, increase the spatial locality. Compiler also used for profiling. So think about, if I can run the program multiple times, I will know all the addresses, right? So the second time I run the program, if I remember the first time, the second time things run much faster, right? So for programs that are run very, frequently in my system, I can have some form of a memory to remember the traces and then provide that to the next time that I run that. I can also use the compiler to provide these kind of tips or guidelines to the hardware that, okay, oh, last time I ran this, here's the addresses, go and, for example, prefetch this. So there's actually tons of things that can happen at the compiler level and software level to make things extra efficient for in terms of cache addresses, so you can actually reduce the number of misses. Okay, so this is, for example, an example of tiling, which is a little bit convoluted, but essentially the design is like, if I have something like this, that if I have like a 4i equal to 1 to the number of rows, 4ij equal to 1 to number of columns, and I basically go through the columns and rows. If the number of columns and rows are so large, okay, what will happen is that, the first few rows might be in the cache, but if my matrix is very, very large, I can only like cache this part of it, okay? So the moment that I actually go after the next row, these are all will be misses, okay? So these are all misses, okay? So what I can do with tiling though is, if I do this, say, okay, this is the size of my cache, so here's how I'm going to actually address this cache. So here's the patterns that I'm going to use. So I'm going to actually work in tiles and work on the quadrants or smaller subset of matrix, make sure that I reuse all those addresses as much as I can, go to the next, portion of the matrix and then use those addresses. There are various ways you can have like what we call row stationary or column stationary. If this is some form of a matrix multiplication, you can also have what we call weight stationary. You can have input stationary, output stationary. Those of you who are like into machine learning and matrix multiplications probably have heard this, but generally the idea here is that I want to reuse lines as much as possible for a very long matrix and reduce kind of like going through random addresses as much as possible. Yes. Yeah. So the most efficient way would be making the tile as big as your level 1 cache, for example. Okay. Another way of reducing the miss rate is the replacement policy. We already talked about this, like LRU versus PLRU versus random. The trade-off there is that, of course, you want to have better replacement policy, but usually better replacement policy requires more storage. And sometimes the storage doesn't significantly increase the accuracy, so you want to find a trade-off there as well. But that's basically it for the miss rate. So these are like different ways of reducing the miss rate. Okay, let's talk about miss penalty and hit time as well. So one way of reducing, so there are a few things on the miss penalty and a few things on the hit time. One way of reducing the miss penalty is using what we call write buffers. So remember that we talked about the fact that, for example, we can, if you have like something like a store, right? And then if you also have something like a load that happens after a store or a store that happens after a load, one way of doing this is that if you don't have any buffering between the CPU and the memory, the CPU has to stall until the operation is done, like the store operation is done. But obviously, that's not a very efficient thing to do. What we do instead is that we have a buffer between the CPU and the memory. And what we do is that the CPU is essentially just write into this buffer. Remember, we call that a load store queues. And then move on. So it doesn't wait to see where this write's going to happen. Is it in L1 or is it in L2 or is it in L3? Is it in main memory? All that. All of those things happen in the background, right? As a result, if the data is not in the cache, you're not waiting for the cache to kind of resolve that. We write it to a buffer, we let the buffer and the cache talk to each other and move on to the next instruction, okay? And this will also help with the future loads because we can always forward that value from that buffer to the future loads. Again, the load doesn't need to go inside the cache to read those things. It can actually check that buffer and boom, it can get that value as soon as possible, okay? So write buffers are kind of like given and very commonly used in any design. Of course, it requires additional complexity in terms of implementation, but as I said, it's pretty standard in all the modern processors have some form of a write buffer, okay? That also brings the question of what should we generally do on store? What happens to the cache when we have a store? Let's assume that we have a write buffer. What happens in this? What happens in the cache in the store? And there are two possibilities. Let's say I want to store a particular address X, and let's say I have only level 1 cache. So I want to store X into the cache, and two possibilities happens. Either the data is already inside that level of cache, or the data is not inside that cache, okay? So what should I do in both cases? If the data that exists in the cache, there's one question that you might wonder, that should I update the memory and cache on every write? Or should I just update the memory, or should I update only the cache? Which one is the better idea? So essentially the idea is this, that this is my level 1 cache and this is my memory, right? So this address X exists in L1, and of course it exists in the memory. Everything exists in memory, right? And now CPU says that, address X, there's a new value for it. So I need to basically update the data, the value that is stored in that address. I have two options. Option number one is that when I'm updating this, I also go back and update the memory, okay? Option number 2 is that I only update this, okay? And don't update this. I only update this when this is actually evicted from the cache, okay? So these are the two possible strategies that I use the cache as a filter. So whenever I'm writing something, I only talk to the cache and I don't talk to the memory. And I only talk to the memory when the data is evicted from the cache, okay? Or when I'm writing to the cache, I also write it to the memory. For this option that I only write it to the cache, I need to keep track whether or not this value needs to be quote unquote written back to the memory. As a result, we usually have this bit called dirty bits. So if the dirty bits is 1, it means that this line is dirty. This line has been updated, so I write it back to the memory when it's evicted. If it's not dirty, then when it's evicted, I don't need to do anything. I just move forward. Yeah.
So like, wouldn't it be the purpose of a cache to write memory and write it? You get what I mean? Like, if we weren't like writing to memory every time we write to a cache, then would that be the purpose of using the cache more efficiently instead of time?
So are you saying that writing to the memory and cache is more efficient, or are you saying that it's unnecessary to write it to both memory and cache when we have the cache?
I'm saying if you have the cache, we also write the memory, write the cache, then that would be the purpose of writing a cache.
Yeah. So the question is, if I have a cache and a memory, and every time I write to the cache, I also write to the memory, wouldn't that defeat the purpose of a cache? Not necessarily, because cache is still very useful for your loads, right? So this is for stores. So for loads, you always read it from the cache and you never go to the memory. We're asking that, okay, if I want to update that value, obviously you need to update the value in the cache. The question is, do I need to also update the value inside the memory or not? Okay. The difference between these two is later you're gonna see the difference. But by the way, the first one that you actually update the cache and memory together is called write through. The one that you update the memory and only when the line is evicted from the cache is called write back strategy. Okay. The reason that you like the write through is, imagine that this line needs to be read into another cache. Okay. If this line needs to be read from another cache, then it's going to take more time to load it into the cache, because now I need to first write it back and then load it into another memory. Later, when we're talking about multi-core, you will see that we have multiple different independent caches. And as a result, when we are loading things from the memory to those caches, write through is significantly faster, because I always have the updated copy of my data in my main memory. I can read them very quickly, versus write back strategy. If I want to read it, I need to first query the other cache and say that, oh, do you have a dirty line? If you do, give me the updated value, and then send it to the other cache. So there's a whole bunch of problems that will arise from the write back. But the nice thing about write back is it saves the bandwidth a lot, because imagine that there is a line that is heavily written by the CPU. Your cache can filter that, so it doesn't need to actually go through the memory. So lots of bandwidth between the cache and memory will be saved by the write back strategy. Yeah. Uh-huh. Uh-huh.
Then what's the big difference? Right.
You're right back, yes.
But then if you're getting to the right back strategy, or it's sort of like where you have multiple caches,
Uh-huh.
then when you want the value of x1, let's say it's 30, one cache,
Uh-huh.
one, let's say x1 turning to another cache,
Yeah.
you have to look to every cache.
Yeah. So the question is about the dirty bits. So when we have the dirty bits and we have the memory, you always just write it back when the dirty bits is 1, and that's great. When we have multiple caches, then things becomes a little bit complicated, because now I need to check every other cache to see if the dirty bits is 1, write it back, and so on. We're gonna actually spend a decent amount of time when talking about this multi-cache environments when we are talking about multi-core. What is the right strategy? Is this the right strategy? Maybe if we can like forward from one cache to another cache. If that's how does that implemented and all that. So we're going to talk about that. This is called cache coherency problem. Yeah, multiple. So for example, let's say I have one core, it has one L1 cache and it has one memory, right? Now I introduce another core that has its own L1 cache. So, and these two are not shared, right? They're like own private caches. All right. Second option is that if the data does not exist in the cache, okay? If data does not exist in the cache, now the question is, should I bring it to the cache or should I just update the memory and move forward, right? So there are two ways that you can do this. If I bring it to the cache, I call it write allocate, which means that when I'm storing address X, and I have my cache and my memory and see that, oh, it's not in the cache, it's a miss, but obviously it is in the main memory. Now the question is, obviously I want to update this, that's out of the question. But now the second question is, should I bring this here? Will I need it in future or not, right? Because that's the question that you need to answer. If you bring it to the cache, you allocate a new line in the cache for that store, we call it write allocate. If you don't bring it into the cache, we call it write no allocate. Okay, so these are two options. Which one do you think is better? Anyone? Should we bring it? Yeah.
I think no allocate is better. I don't know whether. So maybe it's just like.
So we have one write no allocate, but what if we actually do need it? So you're gonna have a miss.
Right.
Yeah. So if you really need it or you think that it's likely that you need it, then write allocate is a better option. But if you don't need it or you think that it's unlikely or it's like, you don't want to pay the trade-off penalty of additional activities, then write no allocate is better. Which one do we use? It's, modern processors use both. It also depends on the multi-cache strategies that we're going to talk about later. But it could be write allocate, write no allocate. It's really there's no like one simple answer for it. Yeah.
You have a statically.
Yes, these things are usually statically determined. Write allocate, write no allocate. Yeah. Yeah, and typically what you will see, and again in modern system, is that write back is often combined with write allocate, and write to is often combined with write no allocate. The reason for it is for write back and write allocate, you assume lots of locality, lots of reuse, right? So it kind of makes sense that you want to allocate if there is a store and you want to keep it in the cache as much as possible. If you think that this is unlikely that it's going to be used, then you do write no allocate and you do write through, because then the memory will be updated and that would be it. So that's kind of like what you will see in most designs. Okay. As I said, how to pick depends. First of all, it might be at different levels, might be different. And then like, simulators is always useful for these kind of things. So imagine, for example, you can simulate this. You can run one-time design a write no allocate. So you design a write allocate and see which one is better. That's one you use. It really depends on the type of benchmarks that you're using. Sometimes either one could be better than the other. Okay. Any questions? Okay. So going back to the miss rate, another thing that helps with miss penalty is what we call early restart. What is an early restart? Remember I told you that we do blocking, right? So blocking means that if I have let's say a block of 8 in my design, so everything is 8 bytes, okay, and let's say the address that I want to read is block byte number 3, so I need the third block in that 8 block thing, okay, and let's say it's not in the cache, it's a miss, okay, so I need to go and bring it from the main memory, okay. So the way that I would bring it is that I bring it byte by byte, right? So I bring the 0 bytes, the first byte, and so on and so forth, depending on the bandwidth. So there are two options. Option number one is that I wait for the entire block to be completed and send it to the cache. And then once the full block is read, then I forward it to the CPU. Okay? This means that regardless of which part of the block, I always have to wait for all the 8 bytes to come. Okay? Early restart means that the moment that the block that you need, for example, in this case 03 comes, forward that block, to the cache and forward that block to the CPU so that CPU can start working, because CPU doesn't care about the rest of the block. We might need other bytes in future. At the moment, it only needs 03. So give 03 the moment that 03 available, give it to the CPU. This is what we call early restart. So the moment that requested byte arrives, forward it to CPU, so allows things to become faster. Nice thing about this is that this kind of decouples the size of the block with miss penalty. If I have 1 million byte block versus an 8 byte block, doesn't matter. Always the time it takes for me to read that byte, that third byte is sort of the same. Usually what we do is that we couple early restart with what we call a critical word first, which means that in this case, I still kind of wasting some time by bringing 0, 0, 0, 1, 0, 2, and then 0, 3. So what I can do is that maybe I can first request 0, 3, get 0, 3, forward it to the CPU, and then in the background, load the other bytes, okay? So usually you have what we call early restart with the critical word first, which means that I look into the actual address, see which offset do I need, I bring that offset first, and then fill in the rest of the blocks that way. And that way it is guaranteed that request always takes the same amount of time regardless of size of your block. So if I have bigger blocks or smaller blocks, miss penalty is always the same for my design. Did you have a question, or did I answer your question? Yeah. Any other question? Okay. All right. So this is like reducing the miss penalty. Another way of reducing miss penalty, we kind of talked about this multiple times. That is adding more levels. So the reason that you want to add more levels is essentially reducing the miss penalty. So rarely in modern caches you will see only level 1. You typically see level 1 and level 2 and level 3. The reason that this helps is, like, you have something like this. The reason that this helps is that if you again go back to this average access time, you will see that if I have multiple levels, essentially what will happen is that this miss penalty will be the average access time of the next level of the cache. And if that next level can store more things, I will basically reduce the miss penalty. So for example, if I have an example like this, then let's say hit time for L1 takes 2 cycles, miss rate is 5%, hit time of L2 is 4 cycles, and miss rate of L2 is 10%, and miss penalty of L2 is 10 cycles, this is basically means that this is the time it requires to access the main memory. What will happen, just one second, what will happen is that in the case without L2, you have the 2 cycles for this plus 0.05 times miss penalty, which in this case is 10 cycles. So your 10 cycles will come here, okay? But then in this case, what you have is 2 plus 0.05 times, and this itself becomes the average access time of L2, which is equal to 4 plus 0.01 times 10, okay? So the difference between these two is that you'll see this number and this number, and then you will see that essentially the one with L2 helps you to reduce the miss penalty significantly. Okay, you had a question there? Why don't we multiply the hit time at? What the miss rate? Yeah. So you can. So the question is about the formula itself. So yeah, you can actually do this way as well. Like hit time times 1 minus miss rate, right? Plus miss time, kind of like, or miss penalty times miss rate, something like this you can do, right? But this would be, the miss time itself would be, this would be miss time, but this would be essentially hit time plus miss penalty, right? So for miss, you have to search first, and that is the hit time, okay? So regardless of whether this data is in the cache or not, you always pay the hit time. But yeah, you drive this and then you'll find it, okay? Yeah, so what does this do is essentially allowing you to, like, adding additional level of cache, allowing you to reduce the miss penalty, because now you like look into lower level cache and you can store a little bit more and then a little bit more and so on. You might ask that, okay, if I can have, let's say, 256 kilobytes of cache, why don't I add it to L1 directly? So make the L1 bigger. Reason for it is that technology doesn't allow you to do that, because if I increase the size of L1, my hit time increases, the power consumption increases, and so on and so forth. That's why you usually design it like this, that you have smaller cache that has a very fast hit time, and then you have additional layers of cache that allows you to kind of like reduce the miss penalty. Yeah. Say again.
Those calculations you did on the slide.
Yeah. Yeah. So essentially you have, let's so look at this, right? So your miss penalty, your average access time is hit time of your level 1 plus miss rate of your level 1 times miss penalty of your level 1, right? And then if I have only one level of cache, my miss penalty of level 1 is equal to memory access time, okay? Okay? Now, if I add a level 2, what will happen is the hit time of level 1 stays the same. Miss rate of L1 also stays the same. What will be changing is that now my miss penalty of level 1 becomes the average access time of level 2. Okay? So now what is the average access time of level 2? It would be hit time of level 2 plus miss rate of level 2 times the miss penalty of level 2. If I have, let's say, 4 layers of cache, this story continues. So essentially, if I write this equation, average access time of my level 2 is my hit time of level 2 plus miss rate of level 2 times miss penalty of level 2, and then miss penalty of level 2 is equal to average access time of level 3, and so on and so forth. At some point, let's say I have miss penalty of level 3, that would be equal to memory access. So if I have 3 levels, I have something. So you can like basically drive these equations. So what is really happening is that by changing this miss penalty to average access time of L2, if this average access time of L2 is smaller than this memory access time, right? Then you are essentially reducing the miss penalty of L1. Okay? That is what is happening. Okay. So now that I introduced multiple levels, there's also this important question that comes into mind. That if I have, let's say, L1 and L2, okay, so I have an L1 cache and an L2 cache, how should I store data? There are two possibilities. Possibility number one is what we call an exclusive cache, which means that if data exists here, I don't store it here. Okay, so I only store it in one level of the cache, either L1 or L2. So exclusive among the levels. You always have it in the main memory, that's the separate story, but between the levels of cache, you only store it in one. The other option is that you can have what we call an inclusive cache. The idea is that since L1 is always smaller than L2, L2 is always storing a copy of L1 inside it. Okay? So this is called an inclusive cache, that whatever I stored in L1, I also have it in L2. Okay? So what is the benefit of each one? Obviously, the exclusive cache is very efficient in terms of storage, right? So you're not storing redundant things, which is great. But in exclusive means that searching is now serialized. I need to search L1 and then I need to search L2, right? But if it's an inclusive cache, all I need to search is the lowest level of cache, right? If it's not in L3, it's guaranteed that not to be L2 and not to be in L1, okay? Again, later, as you're going to see, when we have multiple caches, in order to make sure that the data is not in any of them and quickly find things, being able to find data fast becomes very important. That's why inclusive cache is really nice. But of course, the downside is inclusive cache means that you're wasting a lot of space. Okay, so so just keep that in mind, that this is the trade-off between the two. Okay. Another thing about multiple level of cache is that level 1, we typically have a split between instruction cache and a data cache. The reason for it is that instruction cache and data cache has different spatial locality behaviors, and they require different bandwidth. So instruction, you probably need to bring lots of things very quickly. For data, it's a little bit different. That's why in level 1, we separate instruction and data from each other. So we have what we call an I cache, and we have what we call a data cache. In L2 and L3, we have unified. That is, we can store either instruction or data. The reason for it is that level 1 filters all those differences anyway. In level 2, they are very, very similar in terms of their behavior. So it's kind of like you have one level of filter that distinguish these two. In level 2, if you want to store instructions or data, doesn't matter. In fact, majority of things that you store in level 2 and level 3 are actually data. You rarely store any instructions in your L2 and L3. Okay? And then when you have a prefetcher, or trace cache, usually connected to the I cache, because prefetcher is great to finding the next instruction very easily, versus finding the next data is typically more complicated. And then this is also bringing to another thing that we kind of like talked about early on in the class as well. We have what we call an Harvard architecture and Princeton architecture. Okay, Harvard architecture, when you have like actually separate memory for instruction and data. In most modern systems, you have Princeton architecture, which you have unified design. Okay, so what we have covered in the class is mostly a one Newman model, which everything was unified. So addresses could store data, it could store instructions. Just keep that in mind as well. All right. What else can we do in order to reduce the miss penalty? So I talked about early restart and critical word first. Another way to reduce the size of the blocks is the idea of sub-blocking, okay? So I told you that I need big blocks because big blocks increase the locality. What I can do is I can have the notion of blocks and super blocks, or blocks and sub blocks, where I can say that, okay, some of these blocks can be empty if I want to. So if I really see a nice spatial locality, I bring the entire block. If I don't see nice spatial locality, I only bring part of this block, okay? So I have kind of like the dynamic capability of either bringing large blocks or only bringing the sub blocks. The downside is that now I need to kind of keep track, right? So that is this a sub block or is this a full block? So I need to add extra bits as a metadata stored with every line in the cache. Say that, oh, okay, this is a sub block. It doesn't have all the data. It's only have this sub block, or it has everything together. Nice thing about this, as I said, you can only then bring the sub blocks if you don't want to bring the entire block. Okay. So sub blocking essentially reduce the miss rate and miss penalty. The reason that it reduced the miss rate is because it's reduced the pollution. Okay, so not only reduce the miss penalty, it also can technically reduce the miss rate. But then you need to have separate storage. It's much more complex because now you have like different ways of bringing things, so you need to kind of be able to distinguish between them. Okay. Lastly, how do we reduce the hit time? Reducing the associativity and size helps. We already talked about that. We said that direct map is significantly faster than fully associative. The reason for it is that in fully associative, you have to search many things versus direct map, you only search one thing. And we also said that smaller cache generally faster because reduced capacitance. So reducing associativity and size. Parallel lookup is another thing. We already talked about that as well, that we search data and tag in parallel. We don't wait for tag first and data next. Doing this in parallel allows you to increase the hit time. You can also access ways in parallel as well. That's also what we do. So we don't like do one way at a time. We search all the ways at the same time. This will also increase my hit time, right? So this parallelization helps us to reduce the hit time. And then another thing that we also talked about was what we call speculative load. Remember when we talked about out of order execution and we said that, oh, okay, we have a line that we are not sure whether it's dependent or not. What we can do is that either wait for things to be resolved, which means that it takes a lot of time for us to hit, but we can also issue it speculatively and say that, okay, we assume that there is no dependency between the lines. Let's actually issue, and then if we need to recover and flush, we will do that. So that's also another way to increase the hit time, because essentially you don't need to wait for things to happen. All right. So that's the summary of all these different techniques. For miss rate, we talked about block sizes, associativity, cache sizes, prefetching, victim cache, compiler, and replacement policy. For miss penalty, you use write buffers, you use early restart with critical block first. You add more layers and you introduce sub blocking. And for hit time, you use associativity, essentially using direct map or set associative instead of fully associative. You add more levels, you do parallel lookup, and then you do speculative loads. And this ways you can increase the hit time. So there are a few more, but these are the main ones that you see in like all the modern processors of like how you increase the performance of your cache. Any questions? All right, so let's have a quick break. We'll come back, talk about a new topic. All right, so we're gonna go one step down and talk about main memory. A few things. So this is where we stop for quiz 2. So whatever I said in the first half of this class was included in quiz 2. But starting this module, this is not going to be included in quiz 2. So it's going to be included in quiz 3. And then on Tuesday, we're going to continue talking about this module and other modules. On Wednesday, we're going to have discussion sessions that we're going to review things. So definitely try to have to attend the Wednesday discussion session. We're going to also have additional discussion sessions on Wednesday, like add an additional slot at 4 to 6. So try to attend either 2 to 4 or 4 to 6. That's where we're going to review the topics of quiz 2. Essentially, quiz 2 will be everything after quiz 1. So everything including superscalar and out of order execution and your CA3 and cache, like everything about the module of cache that we talked last week, and then first half of this lecture. Okay. CA3 is also very relevant to your quiz. The deadline is Sunday, so it's after your quiz too, but I'm hoping that most of you are finishing at least most of your CA3 by Thursday. For CA3, pay attention to the assumptions and timings. Important thing is that generally for out of order execution, there is no like one way or laws of physics that say that, oh, you have to retire at this cycle, or there are actually many different ways of implementation. And eventually an out of order execution is just a contract that is like what happens when it really depends on the assumptions and definitions. So you will see, for example, there's a very specific way of that contract. We show it in CA3, but this could be just many other ways of implementation as well. Just keep that in mind. That's also slightly different than the contract that we gave you during the example in the class. So it's like these are different ways of doing things. Just keep that in mind and pay attention to those details. It's one of those projects that you have to kind of read things very carefully. Also, you have to look at the log file and output file very carefully to make sure that the timings are right. And if you see discrepancy between your code and those, look more closely to those discrepancies to try to figure it out. You still have questions, you can post it on CampusWire. There are already quite a few questions about the log file and different sequence of instructions. My suggestion to you is make sure that you read those questions first before asking another question. The reason for it is it might be repeated and people might be very confused. I will also mark them as redundant if I see that they're the same, and ask you to kind of like repeat your questions as a follow-up question to the previous ones. Also, please answer each other's questions. For those of you who already far ahead in the CA3, you can contribute. And I remind you that there is bonus points for those people who are active on CampusWire, right? So it could be you could get points for being active on CampusWire. Yes, sir.
See how active you are. Kind of like Yatsa.
There is, you can actually go into, so the question is like, how do you see your rank? You go to settings and then accounts or something, and there's like your reputation point you can see, and then others I think you can see as well. Yeah. Yes, you need to generate the same output file as the instruction says, and then have a diff for your output file and show that there is no difference. But then when you're uploading it to the grade scope, you shouldn't then generate those. You only should print out the total number of cycles, because grade scope only check for that. If you print other things, you're going to fail the test on the grade scope. So I mean, on Grayscope, again, you can run it as many times. So if it's printed and see that it's not working, it's probably because of that. So just make sure that you're not printing. Yes, sir. Say it again. Yes, if anything in your code is different order than the output code and it's not following the same, you have to make sure that you follow those orders. So you have to fix your code. And then again, it's not that your code is wrong. It's just that you have to follow exactly that. That's what we want you to kind of be able to kind of follow the tiny details, because it's important. Because tomorrow, when you're actually designing this, there is a design team give you a specification. As an engineer, it's very important you can follow every line of that specification very carefully. So it's a good practice of becoming a good engineer. Another thing is code similarity. I allow you to use ChatGPT, that's fine. You can also sit together and write codes, but just make sure that your codes are sufficiently different. We run it through Gradescope, and Gradescope can actually very easily find similarities if you're moving your functions or change your variables and things like that. So simple things like this is easily will be captured. And if your code has long sequence of lines that are similar to others, we will flag it and ask you to provide us reasoning of why, and then if it's still like, similar enough, and then you couldn't really explain why, we need to report it as plagiarism and cheating. So be very careful when you're writing your code. Make sure it's on your own work. There are like a couple of people in CA1 that has large similarity. I'm going to talk to them soon. But just make sure that even if you're coding together, make sure that you are writing your codes sufficiently different and it's your own work. It's very important that your code is not similar to others. And then one thing I saw in the past is that if you're using the same ChatGPT account, for example, and you're downloading codes, your code obviously will be similar, so be careful about that as well. That would also consider cheating if you're sharing the codes. Yeah. You can cite ChatGPT and say, okay, this is generated by ChatGPT. That's fine. Yeah. No, you can use your own ChatGPT and submit it. It's not going to be similar to someone else's code, right? So that's fine. What I'm saying is that if you use a ChatGPT and generate a code, and then someone else also use your ChatGPT and get the same code, then obviously it will be similar, and then it will be flagged by Gradescope. Yeah. Quiz 1 grade is going to be hopefully out by Monday or Tuesday next week. It's like a 40-50% grading, and I'm pushing the graders to finish it. And CA1 also the same. So hopefully all the grades will be out by Monday. We will also release a homework today or tomorrow, and then the solution will be discussed in the discussion sessions on Wednesday. Yes, sir. On the homework, on the caches, so that it will be used for quiz 2. Yeah. And then your quiz 2 will be next Thursday, similar format as the previous. Any questions about the logistics? Okay. So as I said, so again, repeating that this part of lecture is not going to be part of your quiz 2, it will be part of your quiz 3. So we want memory that is both large and fast. We talked about cache performance, the hit time, miss rate, miss penalty, replacement policy, how to improve each of these metrics. So now it's time to actually go one level lower, right? So we talked about, level 1, I cache, D cache, L2, L3. By the way, usually the last level of cache is called LLC. So if you only have one level of cache, your LLC and L1 is the same. If you have two levels of cache, you have L1 and LLC. So if you heard the word LLC, means that this is the last level of cache. Beyond the last level of cache, you have what we call a main memory. As I said, usually the technology for the main memory is DRAM, whereas the technology for caches are SRAM. Okay, so that's the big difference. So there is a huge jump in terms of latency between DRAM and SRAM. So that's why accessing the main memory usually is in order of thousands of cycles, versus accessing the cache is usually in order of hundreds of cycles. Okay? And then we have what we call the disk, which is also a lower level than the main memory, and it's significantly even more, significantly slower than the main memory and obviously the cache. But when we generally say main memory, we think about this as a combined. So from now on, when I say main memory, what I mean is the DRAM and the disk together. Okay, so DRAM disk together is my entire memory. Okay, so when I say main memory, I mean this. So there is a DRAM part and there is a disk part. Okay, the important thing about main memory is that access to the main memory is always a hit. It's not possible that you access the main memory and data is not there, because you only access things that you have in the past, right? So it's like if you don't have that file, your operating system will not show that file anymore, right? So you only access things that you have stored in the past. But of course, internally, there is a difference between the main memory, the DRAM part, and the disk part. So later on, we're going to talk about the difference between these two. But from the cache perspective, It goes to the main memory and always the data is there and it will be brought back to the cache. Okay, just keep that in mind. Okay, so let's talk about the important things about main memory. How do we manage the main memory? What are the important delays? How do we optimize it? So essentially the role of the main memory is storing the program. And when I say program, I mean program includes the data section, it includes the code section, it has the heap, it has the stack, it has all these other things that it might be necessary. So your main memory should be able to store all of that, right? So it's not just the instruction, not just the code, it's all of that, okay? So initially, what we can have is we can have some form of a static way of distributing memory to different programs, okay? And important things about memory is that programs should be isolated from each other. They should not be able to access each other's data. If they do, then the entire system will be broken. That imagine that you open your Chrome and it write things to your Spotify applications and like mess up with the Spotify. So whenever you're opening a Chrome, your Spotify will crash, right? So you want to have perfectly isolated kind of like, programs. Each one should be self-contained and should be stored into the memory. For now, also assume that things are kind of contiguous, which means that if I have program, the beginning and end of that program, including the code and data section and the heap and stack, all are in the consecutive addresses. Okay, so if I have something like this, then things are good. As I said, each program have different regions, the code section, data section, heap section, and so on and so forth. You can also, if you really want to share things, you can also have a special area that you can share. So for example, say that, okay, this area is shared. If you want to, like, for example, share any information between the programs, everyone can write to that part. And this is separate from each program as well. Okay? And then if I have like something like an operating system, I can treat the operating system as also another program and say that, okay, there are some part of the memory is also a reserve for the operating system, okay? And this could be like a small part, it could be a big part, it could be moved and all those things, okay? So now the question with this is that how do we manage this? What is the right way of assigning this? What will happen if like one program is kicking out, the other program comes in? What are the challenges that we are seeing in the system? Okay, this is typically what we call a memory management. Typically, the memory management is done by the operating system. What we call could be also baked into the hardware as well. As we will see later, some of these things are actually implemented in hardware, but most of these things are software managed. So the big difference between the main memory and cache is that cache is mainly managed by hardware. So like replacement policy and searching and all that, they're all done in hardware because it needs to be fast. Main memory though, since it's not fast, it already takes thousands of cycles to access it, there is no reason to develop hardware solutions for it. That's why operating system, which is a software solution, is more than capable of handling things in the main memory. Yes, sir.
Sorry.
Yeah, so for cache, accessing a particular line or searching through cache happens in like nanosecond. Okay, so like takes 10 cycles, 1 cycle. So if you want to use your operating system to decide that, it's very slow because software generally takes hundreds and thousands of cycles to make any decision. So that's why you make things into the hardware. Okay, but when it comes to the main memory, then things are already slow. It's already in milliseconds. So if your operating system is fast enough that can make decisions within milliseconds, then you let the operating system. The nice thing about the operating system is that everything is software. You can patch it, you can write it. You don't need to like make things in the hardware, so the cost is very, very low. Okay? All right, so how do we actually share and how do we manage this memory between multiple programs? That's the story that we want to talk about. So let's say that, for example, the first thing that we can do in order to make things very simple is to partition the memory statically. So let's say I have two programs. I say that, okay, maybe I reserve the first few lines for various different things. But let's say the rest of the main memory say that, okay, this half is for program 1, this half is for program 2. Okay. Nice thing about this is that then the memory management become very simple. Addressing also becomes very simple. Everything is very simple. Two things that I need to provide in this type of memory management is, as I said, I need to have isolation or protection. That means that if program 2 tries to read addresses for program 1, this has to be blocked. So we shouldn't allow program 2 to read anything or change anything from program 1 or vice versa. And the second thing is that my program should be able to run regardless of where it's stored, because in this system, you might store program 2 here, but let's say I download the same program and in another computer, program 2 is stored here, right? So the actual absolute addresses might be different from one computer to another computer, or even when I reboot the system, I might actually load it differently, right? So my program should be able to execute correctly regardless of where it's stored. Okay, so it somehow should be independent from the absolute locations in the memory. Okay, so I need to make sure two things happen. One is the protection. The second thing is location independence. Okay, how do we do that? Essentially, we use two very simple things. For location independence, we use base pointers. Remember, I told you that addresses could be either absolute or it could be like base plus some offset. So I can always like start the program at some base and everything would be offset to that. So any address in my program is always offset to some basic base. So if I move that program, I change that base, everything else stays the same because they're always from relative distance between the base and those addresses stays the same. How do I make sure that different programs don't access each other? I check the bounds. So I essentially define the bounds and say that, okay, program A is in this address range. So for example, let's say address 0x100 to, let's say, 0x2000. So any address that falls within this range is for program 1. And then any address that falls, let's say, between 2000 and, I don't know, 390 something, then this falls into program 2. Okay? So I check this bound. Whenever I'm accessing the memory, I see which bound or which range does this address belong to, and block in case that this address does not belong to the same program. Okay, so I need to kind of like have some form of a program ID, say that, oh, okay, this request is coming from program 1, and I have some form of a table knowing that this ID belongs to this, like this range belongs to this ID. Okay, so more specifically, I kind of have something like this. Okay, so the address comes from the CPU side, and I have two important registers, the bound register and the base register. The base register adds the address that is coming from the CPU, and this way I'm going to have what we call the physical address. So the difference between the CPU address and the physical address is that physical address is actual address that is coming from the CPU plus the base that is the beginning of that program. And then this bound register essentially does this checking. It checks whether we are within that bound that you're supposed to be, okay? And if it's not, then we're going to have a bound violation. What is a bound violation? It could be an exception. It could be an error. It could be a segmentation fault. There could be different things depending on what we have. If you have, like, for example, an operating system, this would be an exception and the operating system will handle it. If a system doesn't have an operating system, this would be, hardware will intervene and maybe reset the system and so on and so forth. But overall, this way we can make sure that we have these two very important things into any program. Any questions so far? Yeah.
So the physical address is just the base.
For now, it's like that. Yes. Yeah, it's converted from just the CPU address, which is assuming addresses start from 0, right? So in CPU, you just start from 0. but in reality, that program might start in somewhere in the middle of your memory. So that base will make sure that you always like offset it from that. Yeah. Yeah, for now, I'm assuming statically, so I know exactly how many programs I have in my memory. So I know the values of all the bounds and all the bases. Okay. But later you're going to see what will happen if I now introduce a new program. What should I do? So this, before actually talking about the dynamic part, this brings a very, very important topic in memory management of main memory, and that is what we call address translation. Okay, typically there is a difference between the addresses that we use in software, in other words, the addresses that CPU uses, versus the actual addresses for accessing the physical part of the memory. Okay. The difference between these two is usually called a virtual address and a physical address. Virtual address are the addresses that you use in your program that CPU deals with it. Physical address are the addresses that are actually like literally physically address that part of the memory and bring that data. For the case like this, that is things are simple and static, the address translation is essentially just means that whatever offset that you have added with the base address, base registers, and that becomes your physical address. So address translation is as simple as just a simple addition. Okay. Later on, you're going to see that this address translation is actually quite complicated because you have multiple programs and addresses are not continuous and so on and so forth. So we need address translation for those. Okay. And then what will happen when we are switching programs? When we are switching programs, you change this base and bound, and then you create a new base and bound, and then you continue, right? So your address translation still works really well. You can switch between as many as programs that your system support, and all it does is that this addresses will change, okay? So that works also great. You might also wonder that under this static systems, what we can do for shared memory and libraries. For example, you have things like printf, standard libraries, you have things like drivers. What should we do? We typically, as I said, reserve part of the memory for those. So usually you give read-only access to all the programs to those addresses, okay? So your bound checking usually is not just a simple bound, but it will be a group of bounds, okay? Then you check that, oh, does it belong to this range, or does it belong to this range, or does it belong to this range? And then you have to check whether or not they have access to those ranges, okay? But typically, if you provide some library, you only provide read-only accesses, okay? So for these accesses, here I'm assuming that everything is a load, but then for a store, I need to, again, check the base and the bound. I also need to check permissions, right? So I need to check whether I can write to this address or can I only read from that address. I'm going to explain this more specifically when I introduce the notion of actual virtual addresses and page tables. But for this very simple system, you can actually add more complexity if you want to by checking these additional bounds and additional permissions. Okay? And similarly, you can have an operating system in this design. And again, operating system would be essentially another program that has the highest privilege. Typically, in order for your operating system to work, your operating system should be able to access everything and anything that you want. So there is no bound checking for the operating system. Okay. There are actually some newer technologies like trusted execution environments that create another isolated memory that even the operating system cannot access it. But for regular systems, for all the modern systems that you have in your access, your laptops, your phones, and so on, this is typically what happens. The operating system has the highest privilege, can access anything and everything if they want. Okay. All right. So that's one option of doing things. But of course, the question becomes, what should we do with when a new program comes, right? When the new program comes, you need to somehow move things around, right? So you need to kind of make up space. You need to remove some space and so on and so forth. Not only that, the second problem that you might have is if you're assigning static space for each program, if one program needs to grow, for example, you have a stack or a heap that needs to grow, or one particular program just needs more space, how do you support that as well, right? So there might be some dynamic changes to the behavior of the program. How do we handle those? In general, how do we handle dynamically this kind of assignments to my main memory? For that, we need some form of a dynamic mechanism that needs to be much more efficient than static memory partitioning. And this is the notion of what we call pages, okay? So what we do is that instead of saying that, okay, here's a big chunk for program 1, and here's a big chunk for program 2, we say that, okay, let's have small fixed size blocks, and we call this a page, okay? And we divide the main memory into multiple pages. So think about like a notebook that has many different pages. And then what we do is that we assign pages on demand to each of these programs. At the beginning, we maybe say that, okay, each program takes 4 pages, okay? And these pages could be different size. Typically, there are 2 kilobytes. There might be 4 kilobytes. There are actually large pages that might be 2 megabytes and so on and so forth. It doesn't matter. It's some size. It's not 1 byte. It's more than 1 byte, because if you have 1 byte per page, it's going to be like, the overhead would be huge. So you want to have some meaningful size for your page, typically in order of few kilobytes. And then you assign few of them to one program. You assign a few of them to other program. You assign a few of them to other program, okay? As I said, for example, you can have 4 kilobytes of a page. Again, since you still want to have byte addressability, now there is another thing that we introduced called page offset, because I still need to be able to read bytes by bytes from the memory. So even if I assign things in the page granularity, I still can read things from the byte granularity. So if I have 4 kilobytes of data, I need 12 bits, because log2 of 4 kilobytes is 12. So this gives you the lower 12 bits of the address is always the page offset in my design, okay? But generally, here's what I'm going to get, right? So the same memory that I had before looks something like this. The pages can be continuous or it could be scattered. Originally, it can be continuous, but if, for example, one program wants to grow, then you want to assign a page somewhere else in the memory, right? So all you need to do is that making sure that the pages, each page is a continuous 4 kilobytes of data, but between the pages, you might have different scattering. So like, for example, for program 1, page 0 might be here, page 1 might be here, page 2 might be here, page 3 might be here, and so on and so forth. An operating system itself can have pages. If you want to share things, you can also have shared pages, and so on and so forth, okay? And then you will have empty spaces in your memory as well. So now that if a new program wants to come, you go through your main memory and see which pages hasn't been allocated to any of the memories. You allocate those pages to those new programs, okay? So this way you can have this very nice and dynamic behavior of paging, okay? And as I said, it could be scattered, and then each page is usually 4 kilobytes. But then this also brings a very, very critical challenge, and that is that now pages could be anywhere in the memory. In the past, I knew that this is my base and this was my bound, but now there is no base, each page could be anywhere in the program. So I need to now kind of like reconstruct my program by these scattered pages and then apply that base and bound. So it makes things significantly more challenging. I also don't know where I stored what, right? So I need to also figure out where, for example, page 1 of program 1 is stored. So that's an additional challenge that I need to fix when I'm doing this. But I really, really need this because without this, I cannot have dynamic behavior. I cannot let the program to grow and shrink and all that. So I need this, but also there need to actually address so many challenges. So how do we keep track? We're going to have a table called page table. That what it does is basically remember where each page is stored. I don't need to remember all the addresses. All I need to remember is the pointer to the beginning of the page, okay? So I will have this table called the page table that basically says that the beginning of page 0 is at address P0. It's just one address, okay? And I know that, the next, whatever P0 is, the next 4 kilobytes is the addresses that belongs to page 0, okay? Then I stored another pointer to P1, and this pointer basically belongs to here. Then I have P2 that points to the beginning of this page, and I have P3 that points to the beginning of this page. And if I have multiple programs, I have multiple page tables. Each one per number of pages stores the beginning of each address. Okay? So that's the idea of what we call a page table. Okay? Okay, so this additional table is just called page table, which is number of rows. Each row has just one address, one physical address. Okay? So essentially the idea of translation is now that you take the address in the virtual memory in the CPU side, you go to the page table, you find the physical address, and that will give you the actual address of your design. So your quote unquote addressing and address translation is that you take a program, you have some address, you find a page number, you find the associated page address to it, and then you access the memory. Okay? So I'm going to pause here, and then the next time we're going to actually continue talking about this address translation, page table, where do you store page table, and all those things. Okay?